for today is really to address the point that Victor ended his talks with. So I'd like to give some sort of framework for identifying Nakajima's construction of simple representations with the geometric Satake construction of simple representations. And I mean, since Victor introduced it already, I'll sort of give away not quite the punchline, but at least the status of the punchline. So what I'm going to say is really an honest theorem in type A, and it's going to rest on some conjectures in types D and E. It will only be for simply laced. OK, so let me remind you of the important points of the setup from yesterday that I want to start from. So I have this conical symplectic resolution. And the example you should have in mind, the simplest example, is the one that has been mentioned a number of times, the cotangent bundle of P1, resolving the nilpotent cone for SL2, which is C2 mod plus or minus 1. So the basic example. Well, this has various sort of structure and conditions implicit in it. It's part of the definition. The part I want to remind you of is that we have torus action on M. So this is a one-dimensional torus. There were two different torus actions, one of which I called T and one of which I called S. I'm not really going to talk about S today. I want to focus on T. And I had a subvariety M plus, which was the points with limits under T. So P and M such that the limit as T goes to 0 of TP exists. And there, in this sort of running example, you should think about well, the 0 section union 1 of the fibers of the cotangent bundle for my M plus. I also had this Steinberg variety, Z, which was M cross M over M0. So again, in the running example, this would be the diagonal copy of T star P1 union P1 cross P1. So in general, it's going to have finitely many components, all of the same dimension, one of which is a diagonal copy of M. But then there'll be some other stuff as well. And I had an algebra A, the sections of my quantization, which was a filtered algebra, non-commutative, such that when I take the associated graded, it becomes commutative, and it becomes isomorphic to functions on M. So back in my running example, so these are all in my examples, here my A was going to be differential operators, global differential operators on P1, which was actually isomorphic to a quotient of the universal enveloping algebra of SL2. So these are the important structures from yesterday that I'm going to refer to again today. Oh, I guess one more thing is category O, the most important thing. So category O, I'll just say some category of A modules. Well, I'll repeat in words the definition without writing them on the board again. I take not all A modules. I take finitely generated ones that are also locally finite for A plus, where the point is the T action gives A an integer grading, and I take A plus, the stuff in grades 0 and higher, and I want it to be locally finite for A plus. That was reminding you what category O was. But the important thing about it was that if I take the Grothendieck group of category O, then I had an isomorphism from that Grothendieck group to the dimension of M Borel-Moore homology of M plus. This thing carried an action of this convolution algebra, the Borel-Moore homology of Z. And we took these convolution operators here and lifted them to operators on the category here. So that's my quick summary of everything from yesterday. So starting now, I'm going to start saying new stuff. The first new thing I'm going to start with is a kind of, not exactly bait and switch, because I'm not really changing anything, but I want to kind of change terminology. So this group, which I've been describing as the Borel-Moore homology of M+, I want to start describing as the dimension D, degree D equivariant, T equivariant cohomology of M. So I could try to spend a while justifying why there's a canonical isomorphism here. Probably the easiest way to think of it is just that both groups have bases given by the components of M+. So the components of M+ are a basis for this group, and the components of M+ are T-stable subvarieties of codimension D, so they also give elements of this group. And with some localization tricks, you can figure out that they're also a basis. So for various reasons, it'll become clear. I'm going to want to think of my Grothendieck group not as this, but as this. Of course, it's completely the same. And the isomorphism here you can still think of as given by a support cycle, microlocal support. Okay. Okay, so I want to look at various subgroups of the Grothendieck group right now. So the first subgroup I want to think about is, well, I'll call it little simples. I want to look at the span of simple objects that are finite dimensional. Right, this Grothendieck group has a basis given by all simples and all simple A modules. Well, simple A modules that lie in category O. And now I want to look at the ones that are finite dimensional, which is some proper subset of the simple objects in category O. And I want to ask, where do they go? Here. They go to some subvector space of this. So where do they go? Well, the answer is, at least it injects into what I'll write won't seem to make so much sense at first, just the degree D cohomology of M. This is a little weird. A priori, this is a quotient of this, not a summand, but it splits by the action of the convolution algebra. So this convolution algebra is acting here and therefore also here, and this quotient is actually an isotypic component for the action of the convolution algebra. So it's a summand, so I'm allowed to think of it as a sum. And this lands inside of here. And even though this is a priori just an injection, I want you to think about it as an isomorphism. So it's often an isomorphism. It'll be an isomorphism in the cases that I care about most. So think of these groups as isomorphic. This sub corresponds to this sub. I also want to think about the dual picture on the right. I want to think about big simples. So what's the opposite of being finite dimensional? It's not completely obvious. Big simples are going to be guys with trivial annihilator. So L simple and the annihilator of L equals 0. So that's sort of the dual notion to being finite dimensional. And where does that go? Well, that goes to the top equivariant intersection cohomology of M0, which is also an isotypic component here. So this is this is naturally a sub, and it's the isotypic component of the trivial representation. It's the stuff in here that's killed by the action of every component of Z except for the diagonal one. The diagonal one acts trivially, and this is the stuff that's killed by everything else. And here, well, it's actually a surjection, but again, I want you to think of it as an isomorphism. So I have this category O, and I have two very natural subspaces of the Grothendieck group, one spanned by the little simples and one spanned by the big simples. And these correspond to the top dimensional cohomology of M and the top equivariant intersection cohomology of the singular guy M0. Okay. So at this point, I want to start making an elaborate multi-part conjecture, which is part of this program that Victor alluded to that we call symplectic duality. This conjecture has a huge amount of structure in it, and I'm going to tell you just enough to be able to relate Nakajima and geometric Satake. So I'm going to tell you sort of the minimum you need to know for my goal in this talk. So this is all due to Tom Braden, Tony Licata, myself, and Ben Webster. Okay. So the first part of the conjecture is that this category O is Cazul. I'm not going to write out a definition, but I'll say it. It means that it has a nice graded lift. So a graded lift of a category, if you think about a category as a category of modules over some algebra, graded lift is like putting a grading on the algebra and looking at the category of graded modules. So it has a nice graded lift. What do I mean by nice? I mean that every simple object has a linear projective resolution. So every simple object can be resolved by projectives so that all the maps in the resolution have degree 1. So that's what it means to be Cazul. And for each of the parts of this conjecture, I want to give you some examples where we know it's true. So the first sort of pioneering example is when I take the Springer resolution. So the causality of the associated category O is due to Bailenson-Ginsburg-Zergel. So this is the beginning of the study of a lot of this stuff. The second example is one that I did not explicitly state yesterday as an example of conical symplectic resolutions. It was a sub-example of something I wrote down, but I want to write it in different language. So suppose I have partitions of a fixed integer, one of which dominates the other. So lambda and mu partitions of R. That means, so partitions of R correspond to nilpotent orbits in SLR. And this means that the closure of the lambda orbit contains the mu orbit. So I want to look at the slice. Well, OK, so I want to say n lambda is the nilpotent orbit indexed by lambda in SLR. And its closure contains n mu. And I want to define x lambda mu to be a resolution of a slice to n mu inside n lambda bar. So these slices are called Slotové slices. It sort of measures the normal direction to n mu inside of n lambda bar. And it turns out these things have resolutions, and they're symplectic. So this is my symplectic resolution. So this thing has a category O associated to it. And this category O turns out to be equivalent to a singular block of parabolic SLR category O, BGG category O. And this is a non-trivial result, and it's due to Losev and Webster. Well, not in a joint paper. Losev did a lot of the work, and Webster sort of finished the picture here. But the point is that these guys, these guys were objects that people knew and thought about before all this geometric category O stuff. And the fact that this category is Cazul that's also in BGS. So this is another example where this category O we got associated to a symplectic resolution turns out to be a category that people already studied in representation theory and already knew was Cazul. It turns out that these varieties are exactly quiver varieties that you get from finite type A quivers. So technically, I did mention these yesterday, just not in this language. The third example is going to be quiver varieties that you get from affine type A quivers. But again, I want sort of more concrete language. And actually, Victor already did this for me. So I want to look at HKR, which is the Hilbert scheme of R points on C2 mod ZK, resolution thereof. And I also want to look at MKR, which is the space of torsion-free sheaves on P2 framed at infinity with rank K and second Chern class equal to R, up to equivalence. So Victor talked about both of these spaces, and he was giving them as examples of quiver varieties you get from an affine type A quiver. So in particular, they're symplectic resolutions. And the category O's here that you get are known to be Cazul due to, well, with certain quantizations called integral quantizations. This is Chang and Miyachi. And the second one, I'm going to write these names a bunch of times, so I won't write them out, but it's Ruquier, Shan, Varignolo, and Bassero in the general case. Prove that these categories are Cazul. So, okay, and maybe the last example I'll write down are hypertoric varieties. So in this case, the category you get is just something we called hypertoric category O, and they're Cazul. Well, we prove it very explicitly in our paper that these categories are Cazul. So this general conjecture, but for lots of examples, we can tell that the category is Cazul. Okay, so now I'm up to part 2 of this conjecture, which is maybe the main part, the meatiest part, and also the strangest part. It says if I have one conical symplectic resolution and its category O, I can always find, by some mysterious means, another conical symplectic resolution, geometrically very different from my original one, such that the category O corresponding to this second conical symplectic resolution is Cazul dual to my first one. So again, I haven't really defined this. Any Cazul category has a dual. And, well, the point is it comes up via some other symplectic resolution. So I'm not going to define Cazul duality carefully, but let me say just very vaguely that it means, so O and O prime, O and O shriek are Cazul dual if, when you look at the derived categories of their graded lifts, these derived categories are equivalent by an equivalence that takes simples on one side to projectives on the other side. So I have one symplectic resolution and its category O, and I can find another symplectic resolution and its category O, which is dual to my original one. Okay, and now let me again sort of go through the list of examples that we know. I'll do the same list. So T star G mod B is dual to, well, I could say itself, or maybe a little bit more naturally, we can take the Langlands dual group. The Springer resolution associated to the Langlands dual group is actually isomorphic to the Springer resolution associated to the original group, but it's more natural to have the duality here. And again, this is from BGS. So the fact that this category O, sort of the most classical category O, is self-dual, or more naturally dual to the category O associated to the Langlands dual group, sort of appears in the original paper. So 2, which is going to be related to this guy, the dual of x lambda mu is x mu transpose lambda transpose. So if lambda dominates mu, then mu transpose dominates lambda transpose, and these are dual to each other. Well, this, I mean, via what's written here, this translates to something called parabolic singular duality. Right? Somehow the category O here, the parabolic is determined by lambda, or do I have it? Yeah, the parabolic is determined by lambda, and the singular part is determined by mu. And when you interchange these, you get something called parabolic singular duality. So in full generality, this is due to Bachelin. And I should be sort of clear about what I mean by these references. Bachelin's work and BGS, I mean, long predate any of this symplectic duality stuff or geometric category O. What I'm saying is, you know, we have this way of associating a category O to a space. That category O is something that has already been seen long before. And the appropriate causal duality between category O's is something that has also already been seen long before. Okay. 3 is that, well, maybe you can guess this, that HKR is dual to MKR. And this actually is not a very old result. This is a relatively recent result due to Ruquier, Shan, Varniolo, and Vassereau. And 4, because I don't want to go into a long combinatorial digression, I'll just write hypertoric varieties are dual to other hypertoric varieties. And this is BLPW. So in other words, a hypertoric variety is defined by some combinatorial input data. And there's some interesting involution on the combinatorial input data, such that you can find a different hypertoric variety, such that the category O's are causal dual to each other. Okay, so I want to move on now to part 3 of the conjecture. So in our conjecture, we don't just expect to find causal duality between two category O's. We expect certain structures on one side to be transported to certain structures on the other side. Right? Just like in geometric Langlands, as we've heard, it's not just some equivalence of categories. We have some Wilson operators here that's supposed to correspond to some other operators here, and stuff like that. So we have various auto-equivalences, involutions that we want to correspond on both sides. And I'm not going to tell you all of that. I'm just going to tell you sort of the part relevant for this talk. Right? If I have some duality between O and O prime, that means that I get a bijection between simples in O and simples in O prime, or O check. I've already sort of told you how this is supposed to work. Really what happens is in the graded lifts of simples go to graded lifts of projectives, but those projectives are minimal projective covers of simples. Right? So I have a simple here goes to the minimal projective cover of some simple here, and this gives me a bijection between simples. And I want my bijection between simples to be well behaved. In particular, I want it to exchange big simples and little simples, and vice versa. So that's one of the many properties that we expect our causal duality to have. And it's true in all these cases. I won't write all the examples this time. So what's the upshot? Let's sort of put everything together that I've written on the board so far and see what kind of cohomological consequences this symplectic duality will have. So if M resolving M0 is dual to M shriek resolving M0 shriek, then I have the top cohomology of M, which, remember, is isomorphic to the span of the little simples. And I want to say that this looks like, I'm being intentionally vague for the moment, it looks like the top intersection cohomology of M shriek 0, which is the span of the big simples in O prime. At least the dimensions are the same, right? Given part 3 of our conjecture, the number of little simples in O is the same as the number of big simples in O shriek. So if I look at sort of the vector space that has that as a basis, that's this. And the vector space that has this as a basis, that's this. I could say that the groups are isomorphic. Really, I think the natural thing to say is that they're dual. Because, as I said, Kazul duality takes simples to projectives. And projectives are dual, form a dual basis to simples in the Grothendieck group. This is slightly complicated by the graded lift issue. But at least what I want you to interpret in this cartoon version is that these two groups are naturally dual to each other. So let me give you an example of this. I want to write down sort of the simplest interesting example, which is a special case of examples 2, 3, and 4 from before. It's not going to be a special case of example 1, because example 1 was about something that's self-dual. So it'd be a little confusing to write that down. I want to write down two different resolutions that are dual to each other, and I want to see this cohomological phenomenon. This is going to be a special case of examples 2, 3, and 4. So on one side, we're going to have T star P2, which resolves, well, it resolves spec of functions on T star P2. I'll tell you what that is. That's going to be nilpotent 3×3 matrices of rank at most 1. 0 or 1. So this is the closure of some SL3 nilpotent orbit, the one defined by the rank being 1. And the dual to that is going to be M shriek going to M0 shriek. And this is going to be C2 mod Z3 resolved. And this is going to be C2 mod Z3. So I claim that this is a special case of parts 2, 3, and 4. So what is this? First of all, this is x lambda mu for this lambda and this mu, whereas this is x mu transpose lambda transpose. Also, this is M31. And this is H31. And also, this is a hypertoric variety, and this is a hypertoric variety. And since I haven't told you how to think about hypertoric varieties, I won't specify the combinatorial input data. Okay. So yeah, let's try to see this a little more explicitly, at least on the level of dimensions. The dimension of H4 of M, the top cohomology of M, well, the top cohomology of M, I mean, the cohomology of this is the same as the cohomology of P2. So the top cohomology is one-dimensional. The intersection cohomology of the singular guy, well, remember my group had two summands. So the Grothendieck group of O was some vector space that was filtered with associated graded the cohomology of M. So my entire Grothendieck group is three-dimensional. And there are two summands, and here's one of the summands, and there's one more, so it's two-dimensional. So the dimension of IH4T of M0 turns out to be two-dimensional. That's a little harder to see if you haven't thought much about intersection cohomology. What happens on this side? Well, if you look at this resolution, the exceptional fiber, the fiber over 0, consists of two P1s that are touching each other. And that gives you the top cohomology. So the dimension of the top cohomology is 2, given by those two P1s. And the intersection cohomology is trivial. So the dimension of IHT 2 M0 shriek is just 1. It's just the constant class. So what happens in this duality, this 1 gets identified with this 1, and this 2 gets identified with this 2. Okay, so now I want to talk about sort of the main goal, the example that relates geometric Satake to Nakajima's construction. So some of what I write down now is just going to be rehashing the constructions that Victor gave, but maybe that's helpful. So G is going to be a simple algebraic group, simply laced, so type ADE. H is going to be a Cartan subgroup. Not T because I'm using T already. X is going to be the weight lattice from H to C star. And I need dominant weights, which are usually called mu and lambda, but I really don't want to confuse them with the mu and lambda that I've already been talking about, which I'm going to come back to eventually. So I'm going to use awful notation. I'm just going to call them xi and theta. So awful just because they're unusual. Okay, dominant weights. So I'm going to be constructing the theta weight space of the irreducible representation indexed by the highest weight xi. So if you can't bear not to call them lambda and mu, well, you can think of this as lambda and this as mu. Okay. So yeah, so my goal is to understand v xi theta, which is the theta weight space of the irrep of G with highest weight xi. So first, let me remind you from Victor's talk how to realize this thing using quiver varieties. Oh, I think for quiver varieties, there's no reason. I think in the geometric Satake picture, there's some reason to make theta dominant, although maybe that's not true and I'm being a little lazy and theta doesn't have to be dominant. I'm just trying to cover myself. Okay, so Nakajima's construction, we have alpha 1 through alpha r in X, which are the simple roots. And we have lambda 1 through lambda r in X, which are the fundamental weights. And these are defined by the condition that when you pair lambda j and alpha j using the killing form, you should get delta ij, so lambda I and alpha j. So just to be a little concrete, when we're dealing with in type A, so if G is SL R plus 1, this is type AR, then X is ZR plus 1 mod the diagonal copy of Z. It's the weight lattice. And here alpha I is a bunch of zeros, and then a 1, and then a minus 1, and then a bunch of zeros. And lambda I is something that, it's a dual basis to this, so it's just a bunch of 1s and then a bunch of zeros. So lambda I pairs with alpha I to be 1, but lambda j pairs with alpha I to be 0 if j is not equal to I. So I want to construct a quiver variety, so I need to use my xi and theta to cook up dimension vectors. And Victor told us how to do this, but I'll tell you again. So define v and w in n to the r by the condition that xi should be the sum of wi lambda I, and theta should be xi minus the sum of vi alpha I. Okay. That's how I translate between my two weights and the dimension vector for my quiver. So let Q be an orientation of the Dynkin quiver for G, so the Dynkin diagram of G. So for example, maybe I take G equals SL4. So my Dynkin diagram has 3 nodes. This is my Dynkin diagram. I want it to be a quiver, so I just randomly choose arrows on the nodes. And I have my dimension vector. I have v1, v2, and v3 here. And then I do sort of Victor's framing trick of adding a w1, w2, and w3 here. So this is the quiver that Victor called Q prime. Right. Keep losing my eraser. Okay. So now I want to look at representations for this quiver with dimension vector v and w. And that has my GLV action, the product of the GLVI's. And it also has a commuting GLW action. And as Victor explained, we construct the Nakajima quiver variety by taking the cotangent bundle of the representation space v and w. Taking the cotangent bundle means doubling all the arrows. And then we mod out by the GLV action. And by mod out, I mean take the 0 level of the moment map, impose a stability condition, and then mod out by the group. I don't know, I could draw 2 or 3 or 4 slashes here. Let me go all out and draw the 4. So I'm going to call this m xi theta. And I modded out by my GLV action, but I still have a GLW action left over. That GLW action is important because remember, I wanted to have a C star action with isolated fixed points. So the GLW is going to sometimes give me my C star action with isolated fixed points. So in fact, it's sometimes true, not always true, if Xi is a sum of minuscule weights, so this always happens in type A, and only sometimes in types D and E. Then there exists an inclusion of T into GLW, so a one-parameter subgroup of GLW with isolated fixed points. So I can do Nakajima's construction without this T action, but if I want a category O, I have to have a T action. So this is only going to work when Xi is a sum of minuscule weights. Okay. So then the theorem of Nakajima is that the top dimensional homology of this group is naturally isomorphic to that weight space. So the top homology of m xi theta carries naturally, well, if I take the direct sum over all theta, it carries an action of g, and it's isomorphic to v xi. And if I look at a particular theta, it's the theta weight space of v xi. So again, Victor mentioned this maybe with slightly different notation in his talk. So this is Nakajima's geometric construction of a weight space of a simple G-rep. So let's sort of remind ourselves about all these dualities and how this all fits in. So I have now the Grothendieck group of category O. That looks like the top dimensional cohomology, top degree cohomology of m xi w, or m xi theta. Oh, sorry, it's the top equivariant cohomology, that guy. Inside it, it has a summand which is the top non-equivariant cohomology. And in here, we have the span of the little simples. And here I said I have an injection, but this is actually an isomorphism. So this is due to Bezer-Kovnikov and Losev, that it really is an isomorphism in this case. So, so my top homology group is now not isomorphic to, but dual to the relevant weight space of the representation. So these guys now are dual. OK, so that was the Nakajima construction. So now let me change gears and talk about the geometric Satake construction. So this all happens with the Langlands dual group. So I have G check, which is the Langlands dual. And it comes with a torus. So H check is the Cartan in G check. And it's Langlands dual to H and G. Okay. And I want to look at the Affine-Grassmannian for the dual group. I guess I'm supposed to write G check of K over G check of O, but I don't want to overuse O. So I'll just write G check Laurent series in Z over G check Taylor series in Z. That's the Affine-Grassmannian for G check. Okay. And I have, so remember X was the weight lattice for G. And I want to realize X sitting inside of GR. So I'll explain how that works. So X is by definition Hom from H to C star. But that's isomorphic to Hom from C star to the dual torus, H check. Right? And this sits inside of H check Laurent series in Z. Right, Laurent series of Z, this is Hom from the formal disk to H check. This is the punctured formal disk. This is Hom from the punctured plane to H check. So, well, a Hom from here determines, a Hom from here restricts to a Hom from the formal disk. Okay. And this sits inside of G check Z, which maps surjectively to Grassmannian when I mod out by this guy. Okay, so X actually lives inside of the Grassmannian. So an element Xi over here, I'm going to call P Xi over here. Where did the big one? There we go. Okay, so this is not just some random subset of GUR. It's actually the fixed point set for the action of H check. So let me explain that. So H check sits inside of G check, which sits inside of this guy, G check of O, or G check adjoins Z. And we've been talking about the action of this group on GUR just by left multiplication. So H check in particular acts on GUR. And an easy proposition, maybe I should call it an exercise since other people have been doing that, is to show that the fixed point set of GUR under the action of H check is actually equal to this set of peak C's. Okay, it's an easy exercise. Okay, so now I want to let straight O Xi, not to be confused with category O, straight O Xi be the orbit of peak Xi. So it's G check Z applied to peak Xi. And now I'm ready to state the geometric Satake isomorphism, or correspondence, which we've already seen in Dima's talk and maybe also in a few others. So the theorem, well, I guess Ginsburg and Mirkovich and Belonin are the two people to put here. So it says that I have an equivalence of categories from G check Z equivariant perverse sheaves on GUR with finite dimensional support. This category is equivalent to rep of G. We've heard that a few times. They're both semi-simple categories. The simple objects over here are the IC sheaves of the orbits O. And the IC sheaf of O here corresponds to the simple representation with highest weight C. Okay. And let's see. Here's a part that we haven't heard yet of this. Over here, I have a functor to vector spaces, which is take cohomology. Right? I can have a perverse sheaf. I can take its cohomology. That's a functor to vector space. Vector spaces. What does that correspond to over here? Well, it corresponds to the functor forget the G action. I just have a vector space. So what does that mean? That implies, in particular, that if I apply this cohomology functor to this IC sheaf, I get the intersection cohomology of the closure of the orbit, OC. This is canonically isomorphic as a vector space to V of C. Maybe I should have, I think somebody wrote bar. I forget if it was an overline or underline, so I'll steal that notation. So this is an object of the category rep G. And this is an object of the category vector space, just given by forgetting the G action. Okay. And, well, I don't really want total intersection cohomology. Remember, I had top equivariant intersection cohomology, not total intersection cohomology. Top equivariant intersection cohomology is a filtered vector space with this as its associated graded. But Ginsburg, in his paper, tells us that we can tweak things a little and get that instead. So Ginsburg explains the following. We can choose an embedding of T, the copy of C star, into H dual, which acts everywhere, and tweak the equivalence, of categories, to get, well, I replace this group with the top T equivariant intersection cohomology of O bar C, and that's now isomorphic to V of C. So this is sort of looking better for us. Okay. Let's see. So now let me just repeat this isomorphism. So V of C looks like IH top T O bar C. And now we can start playing with this group. An equivariant cohomology group we can localize to the fixed points. So this is isomorphic via localization to the direct sum over all fixed points. So remember, the fixed points are indexed by thetas of the top equivariant cohomology of, now I want to take the IC sheaf and I want to pull it back, so just take the Schriek restriction to the theta fixed point. Okay. and this is now isomorphic to the direct sum over theta. Well, this group is exactly the intersection cohomology group of a slice to the theta orbit inside of the Xi orbit. So this is IHT top of slice to O theta in O Xi bar. And of course, this direct sum over theta is supposed to be compatible with the direct sum decomposition of this group over theta. So this is now a direct sum over theta of V Xi theta. So in other words, the theta weight space of G Xi is supposed to be the top equivariant intersection cohomology of a slice in the affine Grassmannian to one orbit closure inside, to one orbit inside the closure of another orbit. Okay, so this is supposed to look like our M0. So now we're supposed to find a symplectic resolution of this slice. Well, it doesn't always exist. It exists. The condition to guarantee that it exists is exactly the same condition to guarantee that we had a nice T action on the quiver variety side. So, in fact, if Xi is a sum of minuscule weights, which always happens in type A and sometimes happens in type D and E, then there exists a variety which I'll call S Xi theta resolving this slice. I'm just going to write slice, but exactly this slice. And this should be this is a conical symplectic resolution. So what's the upshot? We have a quiver variety whose top homology looks like this weight space of a simple rep. And we have a slice in the affine Grassmannian whose total equivariant intersection cohomology looks like a weight space in a simple rep. So now you can guess the conjecture. Now it says that M Xi theta is symplectic dual to S Xi theta. And just to make sure all the dualities work out, let's sort of write down the consequences. So the top cohomology then of M Xi theta would be dual to the IHT top of a slice. This guy this guy tautologically is dual to homology, which by Nakajima looks like V Xi theta. And by geometric Satake, this looks like V Xi theta. So this, if this conjecture holds, then the Cazul duality between category O over here and category O over here has a shadow that sort of relates this identification due to Nakajima with this identification due to geometric Satake via this commutative diagram. Okay, so this is a conjecture. The last thing I want to say is that, in fact, in type A, it follows from things I've already written. So in type A, there exist partitions lambda and mu such that this quiver variety M Xi theta is just the variety x lambda mu. The Sloterdijk slice to one SLR nilpotent orbit inside another SLR nilpotent orbit. So this is due to Maffei about 10 years ago. And this variety S xi theta is isomorphic to none other than x mu transpose lambda transpose. So this is due to Mirkovich and Viburnov. So in type A, the conjectural symplectic duality between this space and this space follows from the honest symplectic duality, essentially due to Baekeland's parabolic singular duality between this space and this space. Okay, I'll stop there.